Okay, so now I've hit record. Oh, hi, Julie. I just noticed you came. Okay, so there are four problems. They're all on dynamic programming. And maybe since C is the one that somebody actually tried, maybe we go to that first. Okay, so C, it's a problem of exact change. This is a very classic problem. So I won't bore you with the document, but basically you have a certain number of, let's say, coins. It doesn't matter if they're coins or bills, but you're given a certain number. So in this case, three different kinds of bills. Each one, the value is listed as follows: 500, 1,000, 2,000. There's nothing here that actually says that these bills are unique. Okay, so this is, imagine this is what you have in your wallet. Okay, you're not allowed to, I guess, say that since they give you 500, you can use 500 as many times as you want. Okay, so these three is what you have in your wallet. Okay, and you're trying to form the sum 1400. Okay, these are all in cents. Doesn't really matter what unit it is. The important thing is that these are integers, so you don't have to worry about decimals and so on. Now, what other things do they tell you? They tell you that each case begins with the price in cents of the items you like to buy, and the price will not exceed 10,000 cents. Okay, so that's one thing that you have to know. The other thing is that there are n lines with the cents of each bill or coin you have. The denominations can be any number of cents, not limited to the values of coins and bills that we usually use in Canada. No bill or coin will have, okay, so this is another important thing. So nothing will be bigger than $100 or 10,000. And the total value of your bills and coins will always be equal to or greater than the price of the item. So you can always buy it. Now, what is it that you want to do? You want to pay for the item that you want, but if you don't have exact change, then you want to pay as little as possible and still be able to buy it, right? So you might have to buy a little bit, you might have to pay a little bit more than what you're supposed to pay, right? So you want to minimize the amount you pay. Of course, you must pay at least as much as the value of the item. And then if you have different ways of paying the minimum amounts, you also want to minimize the number of coins or bills that you pay up. Okay. So that's have two problems in one, I suppose. First, you want to minimize the amount that you pay. And then secondly, if there are multiple ways of paying this amount, you want to pay with the minimum number of coins or bills. Okay, so in the Canadian system, what do you do? Well, in the Canadian system, you typically use what is called a greedy algorithm. What is a greedy algorithm? Always use the largest denomination possible. So, for example, if you're trying to pay 1,000 and then you have something that's so this is the amount to pay, and the bills you have, I don't know, 2,000, 1,500, 700, and so on. Well, you don't use this one because it's too much. You don't use this one, it's too much. This is the largest one possible because it's the largest one that still fits, so you pay it. So now you have 300 left. And then you look down the list for the next one that is less than or equal to 300 and you pay it, and so on and so forth. Okay, that's the greedy algorithm. And it may or may not be the best. In the Canadian system, I guess it's pretty good, but for the most part, if you have an arbitrary system, it's actually not the best. So what do we do? Okay, so you're trying to pay some amount with, I'll just call it S, which is a sum. And the sum, it's anywhere between 0 to 10,000. And then you have bills. Let's just say they're all bills. Doesn't really matter if they're coins or bills. There are n of them. And there are the bills, the amounts are also at most 10,000. Now, did they say anything about how many bills you can have? Let me just see. Oh, they're at most 100 bills. Okay, so this is also important. So N, it's at most 100 bills. Okay, so this is the setup. Now, before we even start thinking about how to solve this, you may have to overpay, right? Because you might not have the exact change, so you may have to overpay. So what is the maximum amount you have to pay? Can you pay $1 billion cents? Or is there some way you can say that you never have to pay more than a certain amount, even if you overpay? Can anybody think of this? Up to, what is the maximum that you ever have to pay? Right? It's obvious, of course, that if you have N bills, 100 bills, each one at most 10,000, obviously you cannot pay more than 100 times 10,000. Okay, that's kind of the obvious one. That means 1 million. But you can be a lot tighter than this. How much what is the maximum amount that you really have to pay? Okay, so let's say S is exactly 10,000. You're trying to pay exactly 10,000 cents. What is the worst that can happen? The worst that can happen is that you manage to you can form 9999, but not 10,000. And then the only remaining bill, it's 10,000. Okay. The worst that can happen is that you pay basically 19999. Okay, you never have to pay more than this. Okay, because if you can form any sum that is bigger than or equal to 10,000, you're done. Okay. If you somehow can pay more than this, if you have to pay 20,000 or more, well, you can take any one of the bills that you used to make the 20,000, remove it, and it will still be bigger than or equal to 10,000. If you take 20,000 minus the amount of any bill, it's still going to be greater than or equal to 10,000 because you know that the amount is no more than 10,000. So if you ever say that you have to pay 20,000 or more, you can always remove one of the bills to pay less and still be able to pay the amount. So you know that you never have to pay more than this much. Okay, that's the first thing to know. So what is our strategy? Our strategy is the following. I'm going to have, okay, I shouldn't, okay, let me get rid of this. I'm going to write f of n s to mean what? The number of coins, well, you're using bills, the minimum number of bills, okay, to form the sum S using the first n bills. Okay, so if my bill, if I'm trying to, my sum is, I don't know, 750, and my list of bills are, I don't know, it doesn't even have to be sorted. and so on. Okay, it doesn't matter. Then, if I want to say what is f, I don't know, what can I form? Maybe something like this. Oh, wait, I'm changing the indexing. So 4 and 20, or f of 4 and 11. So 4 means that I'm allowed to use these 4 bills. So what is the minimum number of bills to form 20? Well, the answer here is actually infinity. There's no way to form the sum 20. Whereas here, there's one way to form the sum 20. The sum 11, and it needs 2 bills. Okay, so infinity means you can't even form that. Not possible. So for every sum, I want to be able to compute what is the minimum number of bills I need using the first n bills to form that sum. So obviously what I want to compute is f of n, where n is the original number of bills, the total number of bills, and s is the sum that you're trying to pay. But what if it's infinity? What if it's not possible to form that sum? Well, if it's not possible to form that sum, then you're going to ask, well, what about this? What if I'm willing to pay 1 cent more? Can I do it? If I can't do it, then I say, well, what if I pay 2 cents more, 3 cents more, and so on? Eventually, one of them will work. So the first one that works, it's the amount that you want to pay, and then the answer is going to be the number of bills that you have to pay. Okay, so does that make sense? Before I go on and talk about how to compute this. Okay, so how do we compute this? So f of ns is what I want to compute. And remember, this is the minimum number of bills to form the sum s using first n bills. So I may not use all of them. I might not use any of them. Okay, so first of all, whenever you have something like this, or you have a function like this, you want to see, are there any easy cases? So if you look at how many ways can you form the sum 0? So that's usually, you say, what is the smallest values you can have for each of these parameters? Well, this is maybe a little bit tricky, but usually the number of ways to form nothing, it's 1, meaning that you don't have to take any bills. Okay, there's exactly one way to form 0. And this is true for all valid n. So if you imagine that this table of f, and in this dimension is n, and this dimension is s, then what I'm saying is that in this first column, when s is 0, all of these entries are 1. Okay, so if I take care of the s being 0, so what about if n is 0? Well, how many ways can you form the sum s if you're not allowed to use any bills? Basically 0 for all s bigger than 0. So we already took care of this, but everything else is 0. Okay, there's no way you can form any non-zero sum using no bills. So basically we managed to figure out the answer for n is equal to 0 and s is equal to 0. And then the important thing is the recurrence. Okay. In general, if n and s are both greater than 0, how do I compute this? Okay, so basically if I'm saying what is the smallest number of bills I can I need to form the sum S using the first n bills. Well, if I have n bills, what I can do is I can say either I use the nth bill or I don't use the nth bill. So if I don't use the nth bill, then it's basically f of n minus 1 s. Okay, so I'm trying to form the same sum, but I'm throwing one of the bills away. I pretend that it doesn't exist. Or the other way is I use the nth bill. So what do I do? If I use the nth bill, then I'll just say amount of nth bill. If I use the nth bill, then what I need to do is I need to reduce what the amount that I'm trying to form with one fewer bill, right? So if I'm trying to form, I don't know, 100, and at the nth bill it's 30, if I decide to use it, then what I do is I subtract the 30 and say that I need to form the remaining 70 using the first n minus 1 bills. And then I have to remember that I use one bill. So whatever this returns, okay, I need to add 1 because I use one more of whatever that is. Okay, whatever I use to form 70, I need 1 more. So either I don't use the bill or I use the bill, the nth bill. Which way is better? I don't know. So take the minimum of the two. Okay. So if I'm computing a certain entry at row n and column s, what do? I look at the row above. This is n minus 1s. And then I look at also the row above this, n minus 1, and then s minus the amounts for n. And then and then add 1 to it. Whichever one is bigger, whichever is smaller, I pick that one. And that tells me the minimum here. Now there are a few couple of important things. First of all, when I say s minus the amount of the nth bill, this should only be used if this is greater than or equal to 0. So for example, if I'm trying to form 100 and my bill is 300, if I try to use it, then now I have minus 200 and now I'm in trouble. So I should not use bills that are bigger than the amount that I'm trying to form. And if you're thinking about the table here, if I do this, then I'll be basically looking out of bounds, okay, to the left of my table. So if the amount of that bill is bigger than S, then it's just this. You don't have a choice to actually use that bill. So you just have to copy this. You have to ignore the second part. The other thing that's a little bit tricky, I suppose, is I said that f of n comma s is equals to infinity if it's impossible to form that sum. So here, this can come back. It may be that this is infinity. Okay, it may be that this comes back as infinity because there's no way to form the sum with the first n bill. And now you try to add 1 to infinity. What does that mean? Well, I guess you can say, well, 1 plus infinity is infinity. What's the problem? The problem is there is no such thing as infinity in computers, right? So you're probably going to pick a really large number to represent infinity, and you better make sure that by adding 1 to it, you won't eventually overflow, right? Because you could eventually overflow. So in this case, what is a good value of infinity? 101 is a good value of infinity. It's a very small infinity, but it's good enough because you know that the number of bills that you started with is 100. So 101, it's bigger than any possible answer you can have. So yeah, it's kind of funny to say that 101 is infinity, but it's good enough for this problem, and it's so far away from the maximum 32-bit integer that you don't have to worry about overflow. Okay, but if you decide to choose, I don't know, the int max, which is the largest 32-bit integers, as the infinity because infinity should be big, then you're going to have to worry about 1 plus infinity because that's probably going to kill you. So you can basically fill this table. You can write it recursively or you can write it in an iterative way. Notice that every time you try to compute something, you always look at the previous row. So if you're filling this table 1 row at a time from top to bottom, whenever you compute something, what you need has already been computed. Okay? And that's it. That will compute the whole table. Now, again, you don't want to, you actually want to compute basically up to this much. Whatever sum you're looking for, you don't really care. You compute all the way to basically the sum that you have plus 1 plus 10,000 or plus the largest coin. Doesn't really matter. You do all of this, and then at the end, row n, you look in this entry, you look at the entry S here, the sum that you're trying to form. If it's a number, great, you're done. But if it's infinity, then you look at S plus 1, and you keep looking until it's not infinity anymore. When it's an actual number, then you know that's the right answer, and this is the smallest thing you have to pay. S plus K, whatever that K is. Okay, that's pretty much all I want to say. So the idea of coin change problem is usually that you have a 2-parameter dynamic programming problem. One of the parameters would be which set of coins, how many coins you're allowed to consider. Not use, you don't have to use all of them, but you have to consider them. Okay, so how many coins are you allowed to consider, and what is the sum that you're trying to solve? And then the base case is usually one or both of these parameters are 0. And then the recurrence is always when you're trying to compute what to do with n coins. You always say, well, what do you do with the last coin? You use it or you don't use it. And that's the 2 branches. And you usually take the minimum. Okay. If you're only interested in knowing whether a sum can be formed, you don't care about how many coins it takes, then this becomes a Boolean value. Instead of minimum number, it can just be true or false. This can be true. This can be false. And then instead of taking a min of these two, it would just this branch, logical, or with this branch, something like that. Okay. Do I want to show you the code? Let me show you the code. Okay, well, I actually use 10,000 for my infinity. Doesn't really matter. So this is basically best ij is minimum number of coins to make the sum I. Okay, so I switched the indices, but it's basically the same thing. So my function, so I have this array that stores my results. So let's go to solve. Solve, what does it do? It reads in all the input, reads in what amount I'm trying to pay, the number of coins, read in all the values of coins. Then I'm going to set my table to be -1 to indicate that -1 means it has not been computed. And then here I have this funny thing that starts for the amount from the amount that I'm paying, that I'm trying to pay. I have this sort of infinite loop. But basically every time I'm trying to say, can I form sum I? If I can, I just print out the answer, I'm done. If not, I come around and I try sum the next one. I keep on increasing the sum that I'm trying to pay until it works. So how do I compute this best IN? It's here. Okay, so if I have no coins, then either the sum, if the sum is 0, that means I can use no coins. Oh, wait, what? Did I do something wrong here? Minimum number of bills. Okay, so I switch in some, this should not be 1 and 0. Sorry. It's actually the number of coins to make the sum 0 is 0. And the number of coins to make sum S is infinity. Okay, so I got this all screwed up. I was mentally doing a different problem. I was doing a problem where I'm counting the number of ways you can form a sum as opposed to the number of coins. Okay, okay, this is more correct. And then, so here I set to be either 0 or infinity whether I can do it. And then this basically says, if I've computed it before, then don't do anything more, just return it. Because remember I said that -1 was uninitialized. Then I have basically two ways. Either I don't use the coin, so the sum doesn't change, or I use the coin. If I use the coin, I better make sure that the coin value is actually less than or equal to the sum that I'm trying to form. If it is, then I basically do this recurrence. I reduce the sum by the value of the coin, use one field coin, and then remember to add 1 to account for the coin that I just used. And then if the coin it's too big, that means I cannot use it. And my trick here is to just make it infinity. So that later on when I do either take the minimum of the two, it basically eliminates this one immediately if you can't use that coin. And that's it. So this is the answer. I set it to the array entry so that if I get asked again next time, I won't have to redo the computation. And basically, what you'd say is you look at here, oops, this table has 200,000, so 2 million entries. And to compute, if every time I call this function, if I have to compute this entry, I do basically a constant amount of work if you don't count the recursion. Okay, I do a constant amount of work, and then recursively, I get some answer, and then I get the result. But why do I not have to worry about counting recursively? Because I know that if I ever computed something once, the next time I would not have to compute it again. It would just return right away. So basically, every entry is computed at most once. There are 2 million entries, so this basically is just roughly 2 million steps, more or less. So this is the standard coin changing problem. It counts how many coins you use to form a particular sum. Any questions? For those of you that are taking 3620, did you look at this particular algorithm or something of that nature?
Not yet, I don't think.
No? Are you doing dynamic programming yet?
Yeah, we just started maybe 2
Okay.
lectures ago.
So what are you guys looking at? I guess everybody looks at Fibonacci numbers. Is that the thing that you look
I think
at?
he was talking about the knapsack problem today. He started working on that.
Okay. Okay, well, that's perfect. Why? Because, hang on, let me try to figure out where this is knapsack. This is my code for knapsack. And the knapsack problem is here. So that's perfect. Okay, so we'll just talk about this one. Okay, so knapsack, classic knapsack problem. You have a knapsack. It has a certain capacity, and you have a bunch of items that you may choose to put in the knapsack. Every item has a weight and a value. So you want to choose a subset of the items, which could be either all of them or none of them, having the greatest value that fit into the knapsack. The sum of the weights of the items you choose must be less than or equal to the knapsack capacity. So you want to put as much, as valuable of items as you can, while not exceeding the capacity of the knapsack. Okay, so input consists of 1 and 30 cases, doesn't really matter. Each test case starts with C, which is capacity of the knapsack, and it's up to 2,000. Okay, so this is a capacity. The knapsack is not more than 2,000. The number of items, it's also no more than 2,000. And then each of the objects has value and weight that are between 1 and 10,000. Actually, the 10,000 is kind of useless for weights because if an object is bigger than 2,000, there's no way that it can be used, right? If the object is bigger than the capacity, there's no way it can be used. But anyway, it doesn't matter. For each case, output a line containing number of items chosen, followed by a line containing the indices of the chosen item. First item has index 0, 1, second index 1, and so on. The indices can be given in any order. Okay, so you're asked two different things. The first thing is, you want to figure out what is the best set that gives you the most value. And then the second thing is you have to produce the actual list of items that you choose. So this is that basically the knapsack that you are looking at in 3620?
Yeah, I think so.
Okay. So here's my code, but maybe I don't want to. Okay, let's switch to the whiteboard. Okay, let me erase everything. So it turns out that knapsack and the coin changing problem are really almost the same. Okay, so what do we have? We have knapsack, capacity, C, and C is up to 2,000. And then you have items, N items, and it's up to 2,000 again. Okay, and then they each have a value. So I'll just call them weight I, which is the weight. Okay, why is my pen kind of randomly moving off everywhere? This is exactly what happened when I crashed just before. Okay, and then your value of the item. So you want to choose a bunch of these objects so that the sum of the weights is no bigger than C and the value of VI is maximized. So what are we going to do? Okay. So we're going to say f of n, well, I'm going to write it exactly the way that I wrote it before, would be the maximum. Okay, hang on, my pen is really not behaving. Why is it jumping? Oh. Uh-oh. Are you guys still with me here?
Yeah, you're still there.
Okay, yeah, I'm still there, but somehow my pen, okay, my pen is randomly jumping everywhere. This is exactly what happened before it crashed. Okay, I'm going to use my mouse instead. Okay, this is going to be a bit challenging for me. So I want to write the max val that I can achieve with capacity S. So if my, this is really not working, writing like this. How am I going to do this? If I turn off my writing tablet and I turn it on again, what is going to happen? Would that work? Universal fix of anything. Turn it off and turn it on again. Somewhat better. Okay, max val with capacity S using, no, this is not going to work. Oh, my pen is really jumping everywhere. Okay, let me forget about the pen. Using some subset of first and items. Okay, this is pretty hopeless writing with a mouse. Okay, so can I, if I use a keyboard, okay, what just happened? Maybe it's easier if I just show you my code, because I cannot. Okay, how do I get? I'm kind of completely confused about what I'm doing here. Hi, keyboard. Okay. Okay, so maybe I'll just show you my code because I can't write anymore on my tablet for some reason. Okay, so basically I have a loop that calls solve multiple times. Why do I have this funny thing? It's because in the original problem, they don't tell you how many test cases there are. You read until there's NFL. So the first thing I do is I try to read the input, which is the capacity and the number of objects. If I'm not successful, that means I have NFL. So I return false, which quits my main program. But if I was successful, then I got to return true at some point to say that there might be more things coming. Then I read in for the n objects, the value and the weight. And then I have I've set this table to be -1, just like before. And then I compute FCN, which says, give me the best thing if I have capacity capital C and using the first n object. Okay, we'll talk about the rest later. So let me just show you F. Okay, so I have this array, best value, which says that it is the maximum value you can get if the capacity of the knapsack is C. So the first index, it's the capacity of the knapsack. And I'm only allowed to consider the first K objects. Okay, 0 to K -1. So this is second index. We'll ignore this second part for now. So my function, it's going to return the maximum value that you can get. Now, this is not actually something that they ask for in the code, but in the question, but you have to compute it. Okay, so if you have already computed it, remember that I set -1 to be uninitialized. So if it's greater than or equal to 0, it means I have computed it. I just return it. If K is 0, that means that I have used all the objects. Then the best value I can possibly have is 0. Doesn't matter what capacity I have. I cannot do anything. The value is 0. Okay, so if it's not one of these base cases, what to do? Well, I can either not use the object. Okay, so if I don't use the object, then the capacity of the knapsack doesn't change. And I just use one fewer object. Otherwise, I want to try using it. How can I use it? Well, that object better be, the weight of that object better be less than the capacity, less than or equal to capacity. If I can use it, then I come in here, then I say, well, okay, if I take away whatever capacity I have, I take away the weight of the last item, because now you have a smaller knapsack now with one fewer object. Whatever is the best value I can get with that setup, add to it the value of the object that I just chose. Okay, because I'm trying to use it, so my capacity is reduced, but my value is also increased because I chose it. And if this one is better than what I already computed, because I already computed it up here, then say, what if I don't use it? They give me some value. If it is better, then I just set the best value to be this one. So again, it's just like before. I try using for this object, I either try to use it or I don't. Those are my two choices. I pick the one that's best. And then at the end, I return. And this will give me the maximum value I can get if the capacity of the knapsack is a certain C and I'm allowed to use a certain number of objects. So down here, when I call f of capital C comma n, I know there's a return value that I'm ignoring, but if I'm actually printing that out, that would be the largest value that I can get with this setup. Doesn't tell me anything about which objects are used. Okay, but it tells me what is the maximum value I can get. Okay, before I move on, does this make sense? Is this similar to what you talked about in your 3620 class? Anybody?
Think so. I think he just kind of started at the end of class today, so
Okay, so you haven't actually
probably,
stepped,
yeah,
you haven't really stepped into the details.
yeah.
Okay, now you have, and what's more, I'm going to show you probably even more that you might not talk about in 3620. So the problem is that here, if I print out this value, the return value of f of Cn, it will tell you the maximum value you can get, but it doesn't actually tell you what you actually chose. You don't know which item you chose. So how do we get that? So what I'm going to say, so remember, how did we get this? How did we get this best value? There are two choices. You can either not use the object, or you can use the object. Those are your two choices. And what I'm going to do is I'm going to remember at each location which one of these two choices gave me the best value. So I have this array chosen Boolean, which basically says corresponding to the best value for CK. In that same setup, did you get the best value by choosing the kth object or by not choosing the kth object? So here, when I compute the best value being not choosing the kth object, I assign it to false by default, because by default, I'm saying that the best value is to not use that object. And then if I go down in this branch and I discover that the best way is actually to use this object, then down here, I'm going to set it to be true. Okay. So each table entry will not only tell me what is the best value I can get with this particular capacity and this many items that I'm considering, it will also tell me to get that optimal value, whether I should pick the kth object or not. And then once I computed this, I have this function called trace, which basically runs through this all over again. So I have a vector of solution that this is going to store the indices of the items that I'm choosing. So at the beginning, it's just empty. And then this trace function, what does it do? I start trace just exactly the same way that I start f. And this trace function will look very much like the way that f works. Okay, so if k is equal to 0, I do nothing. Okay, so if there are no more items to consider, I do nothing. Otherwise, I see if the item is chosen or not. If the item is chosen, then I remembered item k minus, well, the index kth item is index is k minus 1. So I insert it into the vector to say that I remember that I chose this. And then I recurse on this. So notice that this part, c minus w, k minus 1 and k minus 1, it's exactly the same as this, right? The recursive parameters of the two of f and this trace mirrors each other. And then similarly, if I decide if chosen is false, that means I didn't choose it. So I don't have to insert the kth item into my vector. I just recursively call without decreasing the capacity with one fewer item. Again, if you look at the recursive call up here, it's exactly the same parameters. So this is tracing, tracing the solution in dynamic programming. So dynamic programming often asks you to compute the best value of some kind. But then you also have to try to construct the solution that leads you to this best value. And what you have to do then is to have some way to remember how you got the best value. And in this case, it's either you choose it or you don't choose it. So I just remember whether I chose it or not. Okay. And that's kind of the way it works. Am I still online? I think I am.
Yep.
This
Yeah.
Things kind of freezes on me. Okay, anyway. That's oh, my pen seems to be working again. I don't know what's going on. Okay, so this is knapsack. So knapsack and coin change are very similar. You have this idea that you're trying to form a sum, right? So in the case of coin changing, you're trying to form a sum. In the case of knapsack, you are actually trying to form a sum, which is sort of the total amount of weight that you're trying to use, right? So if you think of it that way, knapsack, it's trying to make a certain coin value. If you think about the coin values of each object as the sort of the weight of the item, they're kind of the coin values, and trying to make a form a sum that stays under the capacity. Whereas in the coin change problem, we're trying to make a sum of the coins that try to stay under what was it? 19,999 or something like that. Then the important thing is that with the recursion, it's always the same. You kind of say, well, you have a certain list of objects that you're allowed to use. Either you use the last one or you don't use the last one. That's pretty much what's going on. So both of them are very similar in that way. Any questions? Okay, should I attempt to use my tablet again? Not sure. Okay, now this one, radio commercials. Let's quickly read this problem. So you have some commercials. Of course, blah, blah, blah. So the radio has a commercial break every 15 minutes. Unfortunately, an owner can choose only one continuous sequence of commercial breaks. For example, all breaks from 5 p.m. to 8 p.m. Help them to choose a continuous sequence of commercial breaks such that the profit is maximum. Okay, so what's going on? The first line contains two space-separated positive integers n and p. N is the total number of commercial breaks in a day, and p is the price of one commercial break. So you have to pay to buy this spot. You can assume that n is up to 100,000 and p is up to 1,000. On the next line, there are n separated integers. The ith integer denotes how many students listen to the ith commercial break. There are always at most 2,000 students listening. And basically, they say that the number of people listening, everybody that listened will spend $1 or whatever it is, Swedish crown on pizza. So basically, if you want to buy this commercial spot, okay, you will make $80, but you have to pay $20 to buy this spot. So your net profit for this one is 60. Okay. Now, if you decide to buy these two spots, then you need to pay 40 and you make 86 back. So you only make 46. So somehow the best is 61. So how is it? I don't know. Why is it 61? Let's see. Okay, well, my pen seems to be not working again. So if I have these three, maybe, then the first one gives you 15. The second one, you lose $14. And then the next one, you get 60. So this is how you get 61. Because the first one, you gain 15, then you lose 14. So you're still ahead by 1. And then you make 60, so you can make 61. Now you must buy the contiguous one, okay? So you can't just say, well, only buy the ones that are bigger than 20, okay? Because of course, you don't want to buy 6 because it's going to lose you money. But in order to get you 35, and 80, you have to take the stuff in between. You're not allowed to skip any. So over here, why don't we take 21, right? 21 is also bigger than 20. Well, but I can only make $1 here, but I have to lose $5 to get there. So it actually costs me more to get that $1 than to just give it up. Does that kind of make sense what I'm doing? What the question is asking here?
Yep.
So you basically have oh, now I understand. My whiteboard application crashed, and now my writing tablet is working again. So somehow that whiteboard thing is causing problems. Okay, so of course, computer scientists, what do? When something wrong happens, you restart everything and try it again, and hope that it doesn't do it again. Okay, so here we are. Let's hope that it doesn't do it again. So you have an array. Generally, you have an array up to 100,000. You want to find a contiguous chunk, okay? So that when you subtract minus the 20, that whatever price you have to pay to buy this commercial, the total is as big as possible. Now, it's possible that everything here is less than 20. In that case, what do? You just don't do anything. You just give up. You just say that the maximum profit you can make is 0. Okay, so if every spot is less than the price that you have to pay, then you just don't do anything. So I think you have an array of numbers. Oops. Okay, my writing utensil is lagging again. Oh, shit. Okay, hopefully this is not going to die on me. Okay, whatever numbers they are, whether they are 5 or 10. Okay, this is really not working. I don't know what's happening here. And then let's say 100 and so on. If you want to get that spot, if you want to buy this spot, then what you really want to do, instead of saying 5, this is the profit that this is the amount that you're going to get, what you should change it to is minus the 20 everywhere. Because this is, if you buy this spot, this is how much profit you're going to make. Okay, I'm drawing with my mouse here, which is not very effective. So if you buy the first spot, you're going to make, or you're going to lose $15. If you buy the second spot, you're going to lose $10. If you buy the third spot, you're going to gain $80, and so on. So the first step is actually take your array and subtract the price for each spot. And now you have a new array. And this time now, what you want to do in this new array is to basically find the chunk, the contiguous chunk that gives you the maximum possible sum. Okay, so now this is what is called the maximum subvector. Okay, very bad writing with my mouse. Subvector sum problem. Okay, so you have a array, and you want to find a contiguous chunk in the array that gives you the maximum sum. Of course, if all the numbers are positive, the maximum subvector sum is just the whole thing. You want to get everything. But if they're negative numbers, then you have to say, well, do I include the negative numbers? Because on the other side of negative numbers, maybe I have something really big. And then it's worth going across, even if you have to take some losses, just to include this big one. Okay. And at this point, you have a number of, or maybe you have heard of this, maybe you haven't. At this point, you might say, well, okay, what is the easiest way? Well, I can try all possible starting points of the subinterval, subvector. I can try all possible ending points, start and end, and then add up the sum. And then whichever one is biggest is the answer. If you do it this way, then you basically have an n cubed algorithm, because there's n positions for S, there's n positions for E, and then summing things inside, it's another linear loop. It's not exactly n cubed, it's n cubed over 6 or something like that, but basically it's bigger than n cubed. You can knock it down to n squared if you, when you add things, when you, for example, you know the sum from S to E, and then when you move it E over here, then you don't have to do the sum all over again. You just have to add one extra thing. And if you do it that way, it's n squared, which is still no good. N squared is no good because n is 100,000 for this problem. Okay, so what is the solution? The solution is actually linear time. And I was going to explain it, but because I can't figure out how to draw this array, so maybe I will do what everybody always does when they have a problem. It's look at the internet. Maximum subarray problem in the Wikipedia. Okay, so in computer science, the maximum subarray problem is the task of finding contiguous subarray with the largest sum, blah, blah, blah. There are many, blah, blah, blah. So today's algorithm, here's the algorithm. That doesn't really help you. How do I figure out what is the best way to explain this? Let me attempt to draw this. Let's try the pen again. Okay, the pen seems to be behaving for now. Okay, what I'm going to do is I'm going to scan forward. At every stage, so I have this I that I'm scanning forward. At the beginning, I know nothing. And as I scan forward, I would know more and more. And on the right of the scan, I know nothing. And the point is that as I scan forward, if I scan the whole array, I should know everything. So what is it that I'm going to know? I'm going to remember as I go, as I scan forward, I'm going to remember two things. First of all, the best interval so far. The best interval could be like this. Maybe this interval has the best sum. Okay, maybe not, who knows? It could be anywhere. It could be a single element, could be empty, but somehow I know the best interval so far. But also, so this is A, the best interval so far that ends at here. What is here? Here is where I finish scanning. So somehow I know that if I must end here, that the best interval maybe goes from here to here. Okay, so this is A and this is B. And A and B could be the same thing. It could be that the best interval that ends here, it's also the best interval overall. Okay, so now, so if he is here, how do I make here, how do I slide this bar over so that I scan one more element? I guess it'll be here plus 1. Well, I got to look at this entry. I got to look at this entry and I have to say, what? So that this is, call it capital X, whatever value this is. Well, the best interval so far that ends here must include this one because I have to, when I update here, the best interval must end here. So it must include this newer value x. So b is updated to, I guess, the value of b plus x. So the best interval that ends here will be like this. Include this part. And of course, if this interval, if now this b plus x is bigger than, it's better than this interval a, because it's now bigger, because by adding this x, I somehow have an even bigger value than before, then I update the best interval so far as well. If b plus x is now better. And you might then say, okay, so then you go on next one, you just get this one, then the next x, and then you keep adding it. And somehow we always add it. So somehow we just basically take the whole thing, which is definitely not good. So how does this algorithm work? There's an issue. The issue is that this x can be negative. And in fact, if it's negative, it can be so negative that b plus x could in fact be less than 0. Right? So if you have something like 10, 20, and then minus 100, then by the time you scan to here, right, your best interval so far that ends here was 30. And then when you try to incorporate this in the next one, the best interval is now minus 70. Well, that's no good. Minus 70 is no good. So if this is less than 0, I reset b to be the empty interval. So the best that ends here is just the empty interval that doesn't include anything. And then in that case, the empty interval would just be 0. And you keep scanning. So basically you keep scanning every time you try to add the new element to the best interval that ends here. If that number is ever less than 0, just reset it to be empty, or in other words, set it to be 0. And then you update the best interval so far. And when you finish scanning it, the best interval so far that you store in A, that's your answer. And this is called Kadane's algorithm.
Art, when do we actually update A?
Here. So once you have figured out B plus the best interval that ends here, whether it's just adding X or if it's less than 0, you're resetting to 0, then you update A if this is now better. So maybe now I can show you the algorithm that's in Wikipedia. Okay, this is apparently Python. So okay, so there's a best sum. This is the best so far. This is the best so far, and current sum is the best one that ends here. So this would be A, and this would be B. Then at every step, you're going to scan. So when you just try to incorporate X, so you scan one more, you take the current sum, that's my B, add the X, and then if it's less than 0, just reset it to 0. So this max 0, this just means that if this is negative, you take 0 instead. And then you update the A with the best of A and the current B. And that's the algorithm. So this version will tell you the maximum sum, and then the next version down there will also tell you which subinterval would give you the maximum. So with dynamic programming, often you have sort of an relatively easier way to figure out what is the maximum value. And then you have to do a little bit more work to figure out what is the maximum, the solution, the choice that gives you the maximum. So here the code is a lot longer, but it's, I guess it's not that bad if you read it slowly. And the algorithm, it's linear time. Now, the other thing is, of course, we have a code library. So if you go to code library, there's a whole pile of stuff. Let me go to here. There's something called the index, so you can look up index. And of course, you don't know what you're looking for half the times. But one of the things down here is called vec_sum. Find the contiguous subvector that gives the largest sum. That sounds pretty similar to what we're doing. In fact, it's exactly what we're doing. So then you can go and look up this code and just copy it, I guess. And here it is. So dynamic programming, give an array of integers, find the contiguous vector that gives the maximum sum. If all entries are negative, it returns an empty empty vector with sum equal to 0. Blah, blah, blah. If you want the subvector to be non-empty, then you should first scan for the largest elements in the vector and combine the results. If the sum is returned as well as the start and end position, if start is greater than end, the subvector is empty. Anyway, so this is the code. Here it is. There's some comment. But if you use this code, which is what I did in my solution for this radio commercial problem, I just basically take this whole thing, paste it, and then I read in N and P. I read in the array for each element, I subtract P, call the function, and that's the answer. I don't have to do anything else. So I want to show you this cadence algorithm because you might see this in dynamic programming or in any, you should know how it works anyway. But in the programming contest setting, if you don't know how it works, but you remember that this is actually in the code library, then, well, that's the end of that. You just copy and paste and use it. Make sure you know how to use it, of course. Any questions about this one? So this is another classic dynamic programming problem. So I guess when you start talking about dynamic programming, you might even see some of these as, I don't know, homework problems or whatever. So anyway, if you do, then I guess you're lucky. All right, the last one is a non-standard one. Okay, so you have a game. You have a row of n squares. So number 1 to n. So 1, 2, 3, up to n. You start initially at square 1, and you must jump to square 2. That's the first step. That there's nothing that you can do. But after that, you can either jump forward or backwards. If you jump forward, you must jump 1 square longer than the preceding jump. So if you jump this way, you must go to 4, and then you must go to 7, and so on. Because you jump 1 step, then 2 steps, and 3 steps, and so on. Or you can jump backwards, but if you jump backwards, you don't have to increase the length, you just jump with the same step. So if here, when you jump from 2 to 4, well, your previous step is 2, so you can jump back to 2. And you might say, well, this looks like you haven't actually achieved anything, but you have, because even though you already been in 2, if you try to jump next, you're going to jump to 5 because you came in at step 2. So when you go out again, now you're going to 5. So you might be able to go back to 2 and reach something that you couldn't reach before. Because every time you move forward, you go up by 1. So it's not just about where you are, but also what your previous step is. Okay, so for example, after the first jump, you can jump back to square 1 or forward to square 4. For instance, if n is equal to 6, one possible way to get all the way to 6 would be jump to 1 to 2, then jump back to 1, then go to 3, and then go to 6. Every time he enters a square, Nicole must pay an entry fee. The goal is to go from square 1 to square n as cheaply as possible, write a program that determines the smallest total cost for Nicole to get to square n. Okay, so you're going to have to jump around and visit all these places, and you want to pay as little as possible to get to the end. And also, you want to make sure that you keep track, you follow the rules, right? When you jump forward, you must jump forward one bigger step than before. Jump backwards, you keep the same number of steps. So basically, what you can do is you can say, okay, at every step, you have 2 choices. What are your 2 choices? Either you move forward or move backwards. Those are your 2 choices. So maybe you're doing some search. So one way you can solve these problems is basically try all possibilities. You start from here, you jump the first 2 steps, you have no choice. Then you can decide to jump this way, or you can decide to jump this way. So you try both, and then each one recursively try both and so on. And you can try all of these possibilities. And if you have an infinite amount of program computational time, it will work. You just try all possible ways of running around, and one of them will work. Okay, pick the minimum out of all that works. But of course, you don't want to do that because it's going to be too slow. Now, the important thing though is that you have 2 choices, and then you have to move forward or backwards to where? Where can you go forward or backward to? Right? If I tell you that I'm here, then you can either move forward or go backwards. And I ask you, where do I end up next time if I go forward, and then where do I end up next time if I go backwards? If I ask you this question, what are you going to tell me? What are you going to tell me? Where, if I'm here, whatever it is, then I don't know, 5, if I start, oh, wait, 6, because I start counting at 1. If I want to move forward from 6, where do I end up?
It depends on what you did before.
Uh-huh. So the answer is I don't know, because you don't know what is the number of steps you took before. So what we know is that it's not enough to know where you are, but you need to know the location you are, and also the step count, right? How many steps are you going to take next? Although maybe how many steps did you take before, I guess, the previous step count. Because if I know this now, then this would be location plus previous step plus 1, because I need to take 1 more step than before. And this would be location minus previous step. I must know both of these things. If I don't know both of these things, I don't know what to do. Okay? So what am I going to do? I'm going to say F if you tell me that I'm at this configuration, I'm at this location and the previous step, okay, let me just write it as previous so I don't have to write so much every time. It's going to be the min cost to get to square n starting at location and previous step equals to previous. Okay, so somehow I know this is what I want to compute. So what I want to compute is f of 2 comma 1. Now, why do I say 2 comma? Why do I start with square 1? Because I was already told that the first step must put me in here. First step must go from 1 to 2. I have no choice. And the previous step is exactly size 1. That I also have no choice. So I start from here. But the very first step, you pay a price when you enter a square. So you have to also, if this is my array A and the entry fee, it's in A of I, then I also have to write something like this. This is what I want to compute. What is the best cost starting at location 2, where the previous step is 1, plus the entry fee that I pay to get into this square to begin with? Okay, so that's kind of what I want to compute. So how do I compute this f of 2, 1, or f of anything? So f of anything, oops, what just happened? I crashed that whiteboard thing again. Okay, let me, what do I do? Okay, let me use Zoom's whiteboard. Whiteboard, share. Okay, here's a whiteboard. Hopefully this one doesn't crash. Okay, so where was I? I was trying to say f of location and previous. It's equals to the minimum cost to get to square n from location and previous step was previous. Okay, and I wanted f of 2, 1, because that's how I start, plus the entry fee to step into square 2. That's what I want to compute at the end. Okay, so how do I compute this? So basically, so why do I start writing things like this? Because I have basically 2 choices at each step. Every time I get into a situation, I have 2 choices, and I want to choose the best. And once I make a choice, then I can kind of express what happens after that choice by recursion. And this is sort of something that you have to have if you want to use dynamic programming. But actually, even if you want to do recursive exhaustive search, you probably still want to do this. Anyway, so f of n, anything, it's 0. Okay, so if you're already there, then it doesn't matter what the previous step is. You're already there, the cost is 0. Okay, so that's the base case. Otherwise, if location is less than n, then f of location previous is what? Well, you have 2 ways you can go. You can go forward or you can go backwards. Right, those are the 2 choices. So forward means that you'd go to f of location plus previous plus 1, right? Because you have to take one more step than before. And then you remember that you take one more step than before. Plus the entry fee for entering that square. So A of location plus previous plus 1. Okay. Go backwards. It's A of location minus previous. That's where you end up. Plus recursively, like this. Okay. And you take, just like before, you take the minimum of the two possibilities. Either you move forward or move backwards. Now there's whenever we do something like this, you always have to ask, are these indices making any sense? Remember that you only have squares 1 to n. So if an index, it's out of bounds. So so if you move forward and you move too far, don't use it. Don't use that branch, right? So if maybe you can't move forward, but you can move backwards. Or maybe if you move forward, you move out to the left end, but you can move forward. So this minimum of the two things, you have to be a little bit careful to make sure that the choice that you include in consideration is actually possible. What happens if both of them are out of bounds? So it's possible that your step size is so big that you just can't, it doesn't matter which way you jump, you're going to jump out of bounds. And if that's the case, that means basically that you're kind of stuck. You can't possibly go on to get to square n. And in that case, basically it'll be infinity. Okay, so I'm using the infinity. So whenever I do minimum cost, then I can sort of say infinity to mean that something is impossible. So this is a little trick. And that's it. That's all there is to it. So the main thing is to recognize that in order for me to figure out what's going on, I need to know where I am and also what is the previous step. Then I will be able to figure out where I can go next, and then I can recurse. Now, why is this good, right? And so I can do this recursively, right? But one of the things that I realized, so this is a very important step in dynamic programming. You can write recursive functions like this, right? And if you don't have a certain property, then this recursive function can blow up on you. You can write exhaustive search exponential time that just looks exactly like this. Why is this good for dynamic programming? Because the number of locations is limited to 1 to n. And the number of previous steps that you can take, it's also limited to 1 to n. Why do I say it's limited? Because if it's ever bigger than n, there's no way, doesn't matter where you are, trying to jump more than n plus 1 step, you will always get out of bounds. So there's no reason to consider anything bigger than n. And if you think of it like this, then you'll realize that you can ever call f on n squared different set of values. N choices for the first one, n choices for the second one. So altogether, you can never call this function more than n squared different values. You might call it many different times. Okay, you might try to compute something over and over again, the same thing, but the actual different values that you can call is n squared. And once you realize that, then you can use dynamic programming and say, well, let's just make sure that I only compute n squared entries. And if I remember that I've computed something and somebody asks me again and again and again, I don't do anything more, I just return it. So dynamic programming, you typically write a recurrence like this, and then you ask, what are the possible values that you can put into the parameters? And in this case, there are n choices for the first one, n choices for the second one, so there can be no more than n squared choices altogether. Right? With the coin changing, if you remember, we have something like number of coins and the sum, and then we have this this is, I don't know, 100 up to 100 coins, and this is up to this much that we care about. And then when you multiply them together, it's not that big, right? And it's the same idea that you have to kind of analyze how big, what are the possible inputs that you can put into F. And as long as it's not too big, the total set of different values is not too big, you can use dynamic programming to remember. Okay, before I show you the code, any questions? Okay, so let me share my other screen. So the code is here. Okay, so I have an array phi, and then my F is basically where I am and the previous step size. I have an array that's remember what is the cost. This time I did not initialize the array. So in C++, if you have a global variable, it's automatically initialized to 0. And 0 is never a valid answer in this problem because every square has a positive cost. So I know that if I ever see non-zero, it means it's computed. So this is what I do. If it's non-zero, I just return it because it's computed. Otherwise, oh, I see. I did it in a little bit slightly different way. So instead of saying what is the phi of the square that I'm entering, I'm remembering what is the phi of the square that I just entered. Okay, so anyway, it's the same idea. So if I just entered here, then the phi is just the square. So if I'm already at the end, because I'm using a 0 base, so n minus 1 is actually the end, then I'm just saying, then the answer is the phi of that square. Otherwise, I look at basically, this is if I go backwards, this is where I end up. If I go forward, this is where I end up. If this is in range, okay, so if this is not negative, then I try to go that way. Otherwise, it's infinity. So I use ins max into infinity this time. Now, why am I using ins max? It's okay because I'm using long long. So my ins max is 32-bit max, but long long is 64-bit, so I'm not going to have overflow. Why am I using this? The problem says, actually, I don't know why, because the numbers are actually quite small, 500. I don't know why I'm using max, but I guess it's good enough anyway. Okay, so so then I try going forward. Forward this time I have to step plus 1. If it is in bounds, then I recurse in this way, go to that place. Remember that my step size is 1 more at my current square. If I cannot go because it's out of bounds, then it's infinity. And then I take the answer is just the minimum of the two, minimum T1, T2. Now I do a little funny thing that I take the minimum of T1 and T2, and then I take the minimum of infinity again. The reason is if let's say this one returns infinity, which is ins max, plus something, that would be bigger than, a little bit bigger than infinity. This is a little bit strange to say, but this is bigger than my ins max, which is what I call infinity. So by making sure that nothing is bigger than ins max, then I make sure that infinity is represented by ins max and not anything else. There is a minor thing that probably doesn't matter. I probably don't even need this. And then, so here I move to square 2 because I use 0 base. So 1 is actually square 2 in the original problem. Step size is 1. That's how I start off. And because the way that I implemented here, I keep track of the phi when I enter, not when I leave. So I don't have to add the phi for square number 1 in here, the way that I talk about in my in my whiteboard. Okay, so anyway, that's that. So out of the 4 problems, I would say that knapsack and exact change are very standard. Okay, in fact, most times when you learn dynamic programming, you will learn those just like you learn knapsack. I guess in 3620 you'll learn those, but it will still be good practice to do it, right? Because it's one thing to learn it, and in paper and pseudocode is another thing to actually code it. Especially knapsack, because you have to actually remember what is the set of items that you chose. The radios commercials, that's a maximum subvector problem. It's a pretty common one, but it's usually not one that's taught. I would say that quite often it's one that's not taught and left it as an exercise or assignments for people. And then the fourth one, this one is definitely a little bit more advanced. So those are the 4 problems that I chose. Any questions? No, okay, so the next week, well, okay. This is a practice contest. I guess I set it to start tomorrow morning. It's a bunch of problems on basically, okay, I can't write anymore on my screen. I think I have 4 or 5 problems chosen that are all about shortest path. Okay, shortest path in the graph. And there are different aspects of shortest path. So I think you guys learned this recently. Is that true? Yes?
Yeah.
So that would be good practice, all the different ways you can use shortest path. Then I don't think I chose anything that's overly complicated. So anyway, I think that's not too bad. I'll show you one that's overly complicated. This is one that nope, it's not here. Where is the one that's overly complicated? Open status contest. There's one practice contest that I'm using for the team 1 for practice this week. Here we are. So Joseph has been doing problems, and it's this one. Yeah, you see, Joseph did it in 21 tries. So you have planets like this, and the planets are spinning. You start from here. You wait for the planet to spin around until you line up with this one. You shoot over here, then you wait for the planet to spin. You always have to shoot in perpendicular way, and so on. And then you wait for the planet to spin around, and then you shoot. So somehow you know where you start. You know how fast the planet is spinning. You know your rocket ship can accelerate and decelerate at certain speed, and you start from somewhere and you want to go somewhere. And you can only shoot in straight line. So, for example, if I want to go from 4 to 1, I cannot just go from 4 to 1 like this, because 2 is in the way. I have to go to 4 to 5, wait for the planet to spin around, and then go here. And you have to find the shortest way. So this is basically a shortest path on steroid. You have shortest path problems that you have to figure out how to get from one planet to another. You have to figure out how the graph works, because you have to know which one is blocking which one. You have to know the time it takes. So the edge weights, you have to compute with some kind of physics. And then you have to worry about this, how you spin around. So anyway, this is way more complicated. But essentially, once you figure everything out, you run Dijkstra's algorithm. But of course, it's much harder to figure out everything else before you get to that point. But the ones that I chose for you guys are mostly relatively standard, so it would maybe be helpful to learn to practice what you learn in class. Now, for the So we are actually stepping pretty close now to exam time, right? When is the end of term? How many more weeks do we have?
Last class is on the 12th, I think.
Yeah, so if I look at the calendar, 12, so next week it's 7, so one more week almost, like 2 more weeks, right? So probably we should take a break after with one more. So next week and then the week after, and then you guys are probably too busy for any of this stuff. Now, I know that many of you are taking 3620. So if you have any particular topic that you say you want to see problems on, right? Because you're studying or you don't know what's going on, you have to practice or whatever, let me know, right? Because I have a lot of different problems for just about anything that you cover in 3620. So if you want, so this is shortest path. I can choose whatever else. Yeah. Is there anything else that you guys want me to go into? Any particular graph problems? Minimum spanning tree? I don't know what else you guys talk about. Anyway, if you guys can think of something, just send me a note, right? And I can send you something. Anyway, so that's that. Anything else? No? Okay, hang on. Let me stop the recording.